Hello everyone, welcome back to the Pyromath YouTube channel. Today we will be discussing the British Flag Theorem. This theorem is a little geometry tidbit that can be derived very easily, so we're going to call it today a mini lesson. This geometry shortcut can help students in AMC 8, early AMC 10, and the Math Counts state to chapter level. Again, this topic is in geometry, and it's a little basic compared to other concepts we'll be covering in this channel, but it's very useful and insightful. Alright then, let's get started. Before we learn the theorem, let's take a look at the configuration at hand. The British flag with the Union Jack is on the left side, and it kind of resembles our configuration, the geometric one on the right, and hence the name. So we have a rectangle ABCD here, with a point E in the middle. We also draw in line segments EA, EB, EC, and ED connecting E with the vertices of the rectangle. So let's move on to the actual theorem. So we have our configuration again, and the equation for the theorem below. So the theorem states that EA squared, so EA is our segment right here, plus EC squared, EC is our segment right here, is equal to EB squared, EB is the segment right there, plus ED squared. ED is our segment right there. So opposite sides, the lengths of them squared, the sum of them, they're equal. It seems very intuitive, and let's get to proving it. And to get started, let's go back to the equation. We have to start with one term at least. Okay, let's start with EA squared. When we think about EA squared or any length squared in geometry, what basic or important theorem comes to mind? You should be answering Pythagorean theorem. That's one of the fundamentals of geometry. And it actually is applicable here. You may be wondering, well, where are the right triangles? For those of you who know, Pythagorean theorem states that in a right triangle, the hypotenuse squared is equal to the sum of the squares of the lengths of the legs. So here we do not have a right triangle. When we don't have something in geometry, we want to construct it or add it to our diagram. We could do this one way by dropping perpendiculars from E to each of the sides of the rectangle. So here, if we draw a line from E to AB, and we label this intersection point E1, since EE1 is perpendicular to AB, that's how we're defining E1, EE1A, that angle, is right. And so is that angle. But we need those angles because now we have a right triangle, right? EE1A is a right triangle. This triangle here, it's right. Now we have a place to use the Pythagorean theorem that we were foreshadowing. So let's do that. In triangle, let's change colors. In triangle E1A, what is our Pythagorean relationship? Well, we have EA as the hypotenuse, right? So EA squared is equal to EE1 squared, because that's our first leg, plus E1A squared. All right, so we have EA in terms of some other lengths. For now, it may be irrelevant, or you might be thinking, why are we doing this? But later, when you see the algebraic manipulation, this will come in really cleverly. Okay, now continuing, we have EC squared. That's our next term that we have to look at. And we think about doing the same thing. Okay, so EC. We have to drop perpendiculars to something because that's what we did for E and EA. So we do the same thing down here. Let's call this E2. Okay, so by the same properties, we have that E2C. That's a right angle. That angle EE2C by definition. And so to get EC squared, let's look at this triangle right here. Right, let's look at triangle E2C. Now what's happening in the triangle? EC is the hypotenuse. So by the Pythagorean theorem, EC squared is equal to EE2 squared plus E2C squared. Okay, so now we have relationships for EA squared and EC squared. We could do the same exact thing for EB and ED. And sure enough, if we look at this triangle over here, so triangle E1, B, what do we get? We get EB as the hypotenuse, so Pythagorean theorem tells us the following. Oops. Right? Okay, so now we got EB squared down. What else do we have left? ED squared, right? So, same exact process. We just need a new right triangle. We consider this slim one right here. This one is triangle EE2D. What is the relationship we get here? ED is the hypotenuse, so ED squared is equal to EE2 squared plus E2D squared. Okay, so now we have a bunch of Pythagorean relationships. That's what we wanted. How do we relate them together? Before we jump into some algebra and bashiness, let's do a little more clever thinking here. So consider this figure right here. And in the diagram, it's clear what this is. It's a rectangle, right? How do we know it's a rectangle? Well, we use the definitions we used in the problem. This angle right here, EE1A. Imagine this passes through E. EE1A, that's a right angle because of perpendicular lines. Similarly, EE2D is a right angle. And since ABCD is a rectangle, these guys are right angles too. All of the angles are right angles. That's a rectangle. Okay, so now that we know it's a rectangle, what can we do? Well, one property of a rectangle is opposite sides have the same length. So what opposite sides do we have here? In particular, let's consider AE1. So this one, and the opposite side E2D. If we consider those, well, they're equal, right? So we can just write E1A is equal to E2D. That's it. They're equal. Okay, what else can we do? Well, that's not the only rectangle we have in the figure. There's another one hiding right here. E1BCE2. This is a rectangle by the same reasoning, right? All right angles. And we can use the same logic to get another angle equality. Length equality. E1B, this one over here, is equal to E2C. E1B is equal to E2C. Okay, let's write that down. E1B is equal to E2C. Okay, right now we have a lot of equations, but no way to relate them. Well, not really. Now we use the power of algebra. So let's go to a new page to bash this out. And we start with the following. Okay, so we start with EA squared plus AC squared, because that's the left side of the theorem the equation for the theorem we were looking at before. Well, now we find a couple substitutions or equations with EA and EC in it. So let's plug these guys in. This one over here and this one over here. So I'm going to just plug that in. So that's EA squared. And then E2C squared. Okay. So this is what we had. We just expanded it by using the Pythagorean theorem. Now let's use the relations we found from the rectangles. And we use these two equations here, right above us. And we get E1A is equal to E2D by the first one. So let's just plug that in. And then I'm just going to continue to write this down. We also get that E2C is equal to E1B. E1B squared, right? By the second equation listed above. Now all we have to do is a little bit of rearranging in some parentheses that give us some clarity and neatness. So E1 squared. I'm going to bring the last term into here, E1B squared. Right, I'm just grouping the first and last terms. And then I'm just going to group the second and third terms. The middle two terms. Okay, so all I've done here is just group them in a different way. I'm just rewriting them. But look here. So, okay, E1 squared plus E1B squared. Let's look at just this one. Where have we seen that before? If we scroll up a little bit, that's just that. Exactly. It's exactly that. So what can we do? We have a neat substitution there. And let's put that in. And you could probably see where this is going. The second one, E2D squared plus EE2 squared. Where have we seen that? Right here. For ED squared. Alright then. We can plug that in also. And this is the British Flag Theorem, right? EA squared plus EC squared is equal to EB squared plus ED squared. Let's go check it. Well, that's it. Now that we've proved the theorem and have the theorem itself, let's go and apply it to a problem. Scroll down here. This is our proof. We have this problem here. So this problem is 2014 Math Counts chapter round. It's a number 29. So it's up there, but it's from chapter. So let's read the problem. Point E lies within rectangle ABCD. So the figure I've drawn below, it's not to scale by any means, so it's just a visual representation. Point E lies within rectangle ABCD. If AE is equal to 7, BE is equal to 5, CE is equal to 8, what is DE? Right, what is segment right here, this segment? And express your answer in simple radical form. Okay. Well, this problem is screaming at us to use British Flag Theorem, right? It has the exact configuration we need, and it has many lengths. That's important, right? We don't want just variables in our theorem or equation. So let's just write out the theorem again. EA squared plus EC squared is equal to EB squared plus ED squared. Okay, great. So now let's see what we already have, what the problem gave us. Do we have EA? Sure we do. EA or AE, it's 7. Do we have EC? Yep, we have it right here, it's 8. Do we have EB? Yep, again, it's here 5. Do we have ED? No, that's what the question is asking. So we have, out of these 4 variables, we have 3 of them already, and we need 1 of them. That's perfect. That's how we solve an equation. So EA squared, that's 7 squared. just plugging in the numbers. EC squared is 8 squared. EB squared is 5 squared. ED squared is still unknown, right? That's what we want to solve for. And if we just rearrange, manipulate, solve this equation, so ED squared is equal to 88. ED is equal to the square root of 88, but they wanted it in simplest radical form, so we give them 2 root 22. That is our answer for the practice problem. So we just solved the problem, and usually I would end the lecture here, but I'd like to pose a little challenge. You could say it's another problem. We just dealt with the 2D version of the British Flag Theorem, and now I have a 3D figure in front of you. I'm going to call this the 3D version of the British Flag Theorem. It doesn't really have a name. So we have a cube here. It doesn't have to be a cube. It can be a rectangular prism, but let's just put a point P inside of it. And the vertices of the cube here are A, B, C, D, E, F, G, H. The challenge is, can you find a generalization of the British Flag Theorem to 3D figures, or the 3D rectangular prism we're using here? I'm going to give you a minute to pause and think about it, or write down the equation yourself, but I'm going to write the answer down, not the solution, because that is the point of the challenge. So, for this configuration, we have AP squared, this is going to be kind of long, plus, yeah, it's going to be pretty long, CP squared, plus EP squared, plus GP squared is equal to BP squared. As I'm writing this, you could probably see the elements coming out of the normal British Flag Theorem, the 2D version, and translating to 3D, FP squared. And so there's a couple ways to frame this. This is one way you could do it. If you find others, post it as a comment below, or solve it yourself as a challenge. So this is the theorem that you can prove. I'm going to give you a hint right now. It's going to be Pythagorean theorem, but now I'm going to say considered in 3 dimensions. It doesn't really have to be the Pythagorean theorem. You can call it the distance formula, anything of that nature. And so this is the challenge at the end of the video. I hope I'll see you in another Pyromath lecture. Thank you for attending, and farewell.